Good morning, student. Welcome you again in the second series of this lecture on statistical thermodynamics. In lecture number 2, or you can call it a part 2 of this statistical thermodynamics, today I am going to discuss one of the most important part of the statistical thermodynamics, that is the partition function. In my first lecture, I had discussed the importance of the statistical thermodynamics. I have also discussed the role of macrostate, microstate, different type of systems. But today, I will concentrate only on the fundamental concept of partition function. Today I will not discuss the application of partition function. You all know that statistical thermodynamics is a bridge between the quantum mechanics and thermodynamics, or you can call it is a relationship between the macroscopic properties and the microscopic properties. Suppose I am considering a molecule, and you know that if I am taking an ideal gas, the molecules of the ideal gas do not have same energy, and the total energy can be considered as, of course it depends upon the act, translational energy, rotational energy, vibrational energy, and electronic energy, so on. But the question arises that how the energy is distributed among the different molecules. That is the most important. And that probable distribution of the energy can be calculated with the help of partition function. Now, partition function in statistical mechanics. Before the derivation, I would like to discuss some fundamental aspects of this partition function. There are a large number of applications. In lecture number 3, I will derive one by one different partition functions, like translational partition function, vibrational partition function, rotational partition function, and electronic partition function. And what is the most important aspects? Like quantum mechanics, you know that wave function plays a very significant role. Similarly, in statistical thermodynamics also, all the thermodynamic parameters like internal energy, entropy, free energy, heat capacity can be calculated with the help of this partition function. That is another part. Now, in a nutshell, if you ask me, sir, how that partition function can be described, तो अगेन पहला लेक्चर में मैंने बहुत सारे बुक्स आपके सामने रखा था और मैंने बताया था कि अलग अलग बुक्स में उसकी नोटेशन को अलग अलग तरह से दिखाया जा सकता है, बट मोस्ट ऑफ द केसेस पार्टीशन फंक्शन कैन बी डिनोटेड एज कैपिटल जेड. एक जर्मन सेंटेंस है, जस्ट add sum. I'll tell you. And in some books, partition function, don't get confused, capital Q. Now, sometimes we'll consider the partition function of a system. Sometimes we'll consider a partition function of a molecule, a simple system. So, that can be explained by two types. One is canonical partition function, another is the molecular partition function. अब मैं आपको एक्सप्लेन करूंगा व्हाट इज द रिलेशनशिप बिटवीन कैनोनिकल पार्टीशन फंक्शन और मॉलिक्यूलर पार्टीशन फंक्शन. And of course, it is a dimensionless quantity and that reflects how particles are distributed among different energy levels at a given temperature. मैं अब इसको समझाऊंगा आपको. To sum over all accessible energy state. And in normal cases, that partition function can be denoted as, मैं आपको एक्सप्लेन करूंगा ये कहाँ से आया. Z summation exponential EI by KT. That is, you know that is a distribution Boltzmann function. So, जैसा कि मैं हमेशा करता हूँ, डेरिवेशन के पहले मैं आपको बताता हूँ कि पार्टीशन फंक्शन का जनरल फॉर्मूला क्या है. So, the general formula of partition function, of course, here I am representing the capital Z. So that is canonical partition function. Summation of, I will explain G later on. First I will explain that this part. So here is the energy, because you know that there are different energy levels. And that E is the energy of that particular quantum state, and this Kb is called as a Boltzmann constant. I'll give the value of the Boltzmann constant. आप लोग को मालूम है, in terms of SI unit 1.38 into 10 to the power minus 23 joule per degree. And as I just आपको थोड़ी देर पहले मैं बताया, is the German terminology Z is form of just and sum, meaning sum over state. मैं अभी इसको एक्सप्लेन करूंगा. And now the term G is called statistical weight factor. Statistical, the different quantum state. Statistical weight factor. Very important. और sometimes किसी बुक में इसको डिग्री ऑफ डीजेनरेसी भी बोला जाता है. Suppose there is a energy levels and degree of degeneracy is G is equal to 3, means there are same quantum state. That means the energy level E2 has a statistical weight 3, meaning there are 3 different microstates with same energy, 3 microstates. So it is a very important factor. And you know that in some book you can write like that, summation Gi, if I am talking about the I state, exponential minus E beta or beta E, where beta is equal to 1 by kBt. You all know that K Boltzmann constant is equal to R universal gas constant divided by Avogadro number. This is a very common thing. So statistical weight, it tells how many ways a system can be particular state. So this is the general formula of partition function. और मैं अगर अब इसको मैं डेरिवेशन में जाऊंगा कि इसको हम कैसे करेंगे. Now the partition function indicates the mode of distribution of particles in various energy levels. The partition function is a measure of the escaping tendency of the molecular form. मतलब आप population of distribution of energy among, like if I write that suppose there are different energy state, मैं छोटा करके यहाँ पे दिखा रहा हूँ. मैं छोटा करके यहाँ पे दिखा रहा हूँ. And you know, if you understand that quantum mechanics का अगर आपने अच्छी तरह से पढ़े होंगे तो आप you know that what is the concept of ground state and there is a concept of 0 point energy. 0 point energy. You know all these things. So suppose this is E1, then E2, and there are some molecules, different types of molecules. I am saying that molecules may be identical or molecules are indistinguishable. So in some case it is also possible that color is different. One is green color, indistinguishable particle. Another is a red color is also possible, distinguishable particle. Yellow color. So depending upon the, if I just want to energy, another term is the Boltzmann function. E by kBT. So this is also temperature dependence. In some cases, the value of energy is greater than the kB. So the population is difficult at absolute zero or a very low temperature. But if we increase the temperature, so again there is a possibility some molecules can move this side, some molecules move this side, like this side, like this side, like this. So these molecules can move. So these population, when all the particles in the ground state, so we consider that the partition function may be 1. And then if we increase the temperature and other things, so with the help of that partition function, that most probable distribution can be obtained. So that is the simple concept. And you all know that, just I told you that I am consider a particular ideal gas and there is no repulsion and attraction among the molecules, and that energy can be separable, and that total energy at particular, because I am talking about the canonical ensemble, and in my first lecture I have already discussed what is canonical ensemble. You all know that number of particles is fixed, energy is also fixed, temperature, volume is also fixed, NVT. So that is electronic energy, vibrational energy, rotational energy, translational energy, and nuclear energy and other things. So total energy is the sum of electronic energy, vibrational energy, rotational energy, and other. But if I consider the partition function, it is a product. That means partition function of rotational, partition function of vibration, partition function of translational, partition function of electron. And it is of course as per the Born-Oppenheimer theory. I am talking about the different types of quantum state and the energy. But now I will discuss the derivation of partition functions. So you know that total number of particles of a system is n, and that, or I can call it summation of ni, because there are a large number of a gas, different molecules. It may be 1, 2, 3, 4, like large number of, it is just a symbolic things. And my objective is that how I calculate the total number of particles, the distribution. And of course, you do agree with me that this is a great theories of Maxwell-Boltzmann statistics, and it was discovered during 1870. But when J. Willard Gibbs have written very good books regarding the fundamental concept of statistical mechanics, he has slightly modified that equation, and on the basis of that equation he derived the partition function. आप बोल सकते हैं कि ये क्लासिकल मैकेनिक्स से मैक्सवेल बोल्ट्जमैन डिस्ट्रीब्यूशन ऑफ मॉलिकुलर वेलोसिटीज, अब उसको हम लोगों ने स्टैटिस्टिकल मैकेनिक्स में कैसे कन्वर्ट किया, दैट इज द सिंपलेस्ट डेरिवेशन ऑफ partition function. And let me confess that I have taken this derivation from the book of Statistical Thermodynamics, Thermodynamics for Chemists by Glaston. Thermodynamics for Chemists by Samuel Glaston. That is the simplest derivation of partition function. मतलब again, if you are talking about the different energy levels, I, J, K, different types of energy levels, and the probability of distribution can be calculated with the help of this Boltzmann function, and of course the energy difference. So now I will proceed for the derivation, which is again and again I am saying it is based on the books Thermodynamics for Chemists by Glaston. Now, simple derivation. Let me first use this simple. A system consists of n, and suppose there is a excitement and there is a change in population, and with the help of simple Boltzmann distribution we can calculate these things. N0 is the ground state, and here also I am just written here E, I, oblique KB and T. And so this is based on the classical mechanics. Now Gibbs slightly modified that equation using statistical weight factor. So what is the modification? It's very simple. Ni is equal to N0 divided by G0. It is statistical weight factor of the ground state. Then Gi, statistical weight factor of that particular state, I state, quantum states, exponential EI KB absolute temperature. So what is the difference? Difference is only that here we have introduced this term statistical weight factor को इसमें introduce किया गया. Now I am thinking a different system, summation of, because there are a large number of systems, Ni is equal to N. So you can call it N is equal to, there are various systems, N0 molecules, N1, N2, dot dot dot, so many systems, Ni system. Do I make my point clear? एक सिस्टम है जिसमें इतने सारे अलग अलग मॉलिक्यूल्स N1, N2, N3. Now I will write the values of for each system. So I can write like that. N is equal to N0 means N0 G0 exponential minus E0 divided by KBT. Now in some books that you can write in place of EI. There is no problem. It is up to you कि आप इस तरह से लिखिए या इस तरह से लिखिए. मैंने अभी आपको जैसा बताया कि कुछ बुक्स में एक्सपोनेंशियल माइनस बीटा EI भी आप लिख सकते हैं. बीटा इज इक्वल टू 1/kT. आप जो लिखना चाहें आप लिख सकते हैं. 1.38 to 10⁻⁻23 joule per degree, like that. Anyway, so plus for N1, N0, G0 is common. So exponential, if I write G1, E1 KBT. Like for 2 is also like that. For 3, for Ni, N0, G0, Gi exponential minus EI KBT. EI. So like that. So should I write like that? If I take common, N0, G0 is common everywhere. I can write G0 exponential E0 KBT. I should write yellow color also. Plus again for I can write G1 exponential minus E1 KBT. Plus I have not written here G2, but I can write G2 exponential E2 by KBT dot like that. There are so many systems. Plus N0 G0, oh sorry, Gi exponential EI by KT KBT. Is it clear? So now I'll just, because sorry of time, I'll this part. So look here. Now what is this? This part is the contribution of ground state, then 1, 2, 3 or 4 or like that, large number of particles. Condition is that there is no interaction, no repulsion, no attractions. So what I can write like that, N is equal to N0 G0 is equal to summation. Suppose I would like to use all these things, sum of all these states. From I is equal to 0 to maybe I is equal to infinite. Gi, Ei, maybe large number of states, Kb, T. So in place of, again now what is my objective? हमारा objective यह है कि distribution of most probable distribution of molecules, energy distribution कैसे अलग अलग molecules में हो रहा है, और इसको अगर हमने एक साथ sum कर दिया, and what is important, you can, if you want to reference, I am using S. Glaston. सबसे simple derivation पार्टीशन फंक्शन का इस बुक में दिया हुआ है, थर्मोडायनेमिक्स फॉर केमिस्ट, थर्मोडायनेमिक्स फॉर केमिस्ट। बहुत पुरानी बुक्स हैं तो इसमें, और इसको स्टूडेंट को, चूँकि आप लोग कुछ हिंदी मीडियम के भी स्टूडेंट हैं, आप लोग को समझने में एकदम आसान हुआ कि सम ऑफ दिस थिंग, सम ऑफ थिंग्स। सो what we can write, that this whole term this whole summation terms can be written as capital Z, or you can write capital Q, and that is called partition function. Partition function. As because it composes of a system, so it is canonical. अभी मैं आपको समझाऊंगा कि व्हाट इज द डिफरेंस बिटवीन मॉलिकुलर पार्टीशन फंक्शन एंड कैनोनिकल पार्टीशन फंक्शन। और आप नट सेल में समझो कि स्टूडेंट को कंफ्यूजन होता है कि कैपिटल जेड एंड द स्मॉल जेड इज द मॉलिकुलर पार्टीशन फंक्शन। अभी मैं समझाऊंगा आपको कि दोनों में रिलेशन क्या है, मॉलिकुलर पार्टीशन फंक्शन। इसलिए बहुत सारे बुक्स में, इफ यू सी दी लेवाइन फिजिकल केमिस्ट्री Z कैपिटल Z, इफ यू सी दी एटकिंस, किसी बुक में Q एंड स्मॉल Q आप लिख सकते हैं। तो आपको समझ में आ गया व्हाट इज पार्टीशन फंक्शन। मैंने अलग अलग लेवल्स को लिया और अलग अलग लेवल्स को, उसकी समेशन, किस तरह से ये डिस्ट्रीब्यूशन होता है, उसको पार्टीशन फंक्शन बोलेंगे। एंड द लास्ट पार्ट, सो व्हाट शुड आई राइट, सम सिग्निफिकेंस इज इंपॉर्टेंट। सो I can write n is equal to n0 and g0 is the statistical weight factor and it is the ground state का molecules, capital Z, or I can write, you see in red color, what I can write? N divided by Z is equal to N0 divided by G0. Do I make my point clear from that simple derivation? मैं क्या लिख सकता हूँ? ये देखिए, N is equal to N0, G0 and Z or capital Q. I have just rearranged it. So N divided by Z is equal to N0 and G0. Now substitute this value of N0, G0 in your main equation. In your main equation, that is here. It is your main equation. So अब यहाँ पे आ जाइए। So again I am using blue color so that you can understand. So Ni, मैं थोड़ा बड़ा करके लिख रहा हूँ, is equal to Ni, it is I may be quantum state, and you can write J. In place of N0 I can write N, total number of molecules system of a ideal gas, capital Z, Gi exponential Ei kBT. Just imagine again, if I rearrange this equation, should I write in red color? that Ni, particular quantum state, divided by total, it is a probability. एक क्लास में 50 स्टूडेंट बैठा हुआ है, उसमें से पॉपुलेटेड हुआ Ni, so it is a fraction probability. Ni is equal to 1 by Z. That means this probability is reciprocal to that partition function, and it is equal to Gi exponential Ei upon Kt. Now, if I am talking about the ground state condition where the energy difference is 0, you all know that exponential of that 0 is equal to 1, isn't it? So I can write final equation. आप लोग जाके ग्लास्टन को अच्छे से पढ़ेंगे तो आपको समझ में आ जाएगा, या लेवाइन को पढ़ेंगे तो Ni, अभी मैं इसकी समझाऊंगा आपको, 1 by Z. So Z never be 0. Partition function may not be 0. It is always 1, or as per the, if I just change the value, it may be large quantity, it may be very small quantity. If it is 0, then it is 1. If it is large quantity, maybe 1. That means, so it depends upon various factors. So with the help of this simple formula, this is the probability, the significance of partition function can be explained. लेकिन आप कभी कभी आपके मन में प्रश्न आता है, सर व्हाट इज द रिलेशनशिप बिटवीन मॉलिक्यूलर पार्टीशन फंक्शन एंड कैनोनिकल. अभी मैं इसके बाद मैं इसको समझाऊंगा, पहले मैं आपको अभी थोड़ा सा सिग्निफिकेंस ऑफ पार्टीशन फंक्शन बताऊंगा, फिर आई विल टेक ओनली 5 minutes टू एक्सप्लेन द रिलेशनशिप बिटवीन दी, ये बड़ा Z है या बड़ा Q है, इसको हम लोग कैनोनिकल, क्योंकि होल सिस्टम को बता रहे हैं, कैनोनिकल पार्टीशन फंक्शन, एंड द स्मॉल Z स्मॉल Q इज द मॉलिक्यूलर पार्टीशन फंक्शन. कैनोनिकल एंसेंबल आपको मैं फर्स्ट चैप्टर में ये n again and again the condition is that particle must be distinguishable, मतलब एक दूसरे से अलग हो सकता है. If it is an indistinguishable particle, that may not be valid. मैं आपको उस पॉइंट में आऊँगा. So you follow this point that what I am getting, Ni by N is a probability fraction, 1 by Z is a reciprocal to this. So what I can say that Q or Z summation of I is equal to 0 to I is equal to infinite Gi E Ei Kb and, or as I told you that beta this is simple formula of the partition, or you know that it I have already told you 1 by kVt. So the significance, इससे हम क्या निकाल सकते हैं? So that again and again I am saying same thing, Ni you see divided by N 1 by Z. Because if I am talking about the ground state where the exponential value is zero value, so therefore, so it is a reciprocal of the fraction of particles occupying in the ground state. So ratio of the total number of particles in a system to the number of particles in the ground state counting the probability of the things. Now, question arises, very objective type question may be asked. If we increase the temperature, what happens? And if the values of delta E, whatever the change in energy among these different energy levels, so sometimes ये भी हो सकता है कि the value of this delta E is equal to kBT, ये भी हो सकता है. ये भी हो सकता है कि वैल्यू ऑफ डेल्टा और वट एवर दी ये जो एनर्जी है बहुत ग्रेट. ये भी हो सकता है कि आपका ये वैल्यू की, ये भी हो सकता है, डिफरेंट टाइप्स ऑफ कंडीशन. सो दैट इज द सिग्निफिकेंस ऑफ. सो इट इज ए नंबर. Partition function is a number, maybe value may be very high sometimes. It is a dimensionless and it tells the mode of distribution of particles in various energy levels. अब आपको समझ में आ गया. When all the particles in the ground state, जैसा अभी आपने देखा for electronic partition function, when the temperature is raised, the particles is occupying the higher state. फिर वो धीरे धीरे and that population can be calculated with the help of the partition function. So it can be applied to a system of any physical state. Now if T is infinite, is important, that is also infinite. So the partition function provides an indication of the average number of molecular state accessible at a given system of the temperature. So in my third part, when I will discuss various partition function, आज मैं केवल इस लेक्चर में आपको मैं केवल पार्टीशन फंक्शन क्या होता है, पार्टीशन फंक्शन की डेरिवेशन, उसकी डेफिनेशन समझाने की कोशिश किया. और थर्ड लेक्चर में मैं एक एक पार्टीशन फंक्शन को अलग अलग आपको डिराइव करूँगा, उसका कुछ न्यूमेरिकल प्रॉब्लम्स भी कराने की कोशिश करूँगा. अब इसका मैं लास्ट पार्ट में आ रहा हूँ कि हाउ वी से दैट दिस कैनोनिकल पार्टीशन फंक्शन और मॉलिक्यूलर पार्टीशन फंक्शन में क्या डिफरेंस है. और फिर से मैं आपको बता रहा हूँ कि बिकॉज देयर आर मेनी बुक्स अवेलेबल इन आवर लाइब्रेरी, इन द डिजिटल नेटवर्क एंड इंटरनेट. सो it is up to you. You can use capital Z, you can use capital Q, whatever you want. Now I will derive that how we will get this Z is equal to Zn. So it is just a very small system. So what I will do now, the relation between capital Z canonical, and for that I have to take a particular system, and there are two ensembles, A and B, and distinguishable. BLE, distinguishable, non-interacting. So again I'll just use capital Z is equal to summation GI, you can write like that, exponential minus beta E. And suppose this energy of this particular ensemble for A, it is epsilon AN. For B system ensemble, it is energy B and N. N may be quantum 0, 1, 2 like that. So what I can write? I can write Z is equal to summation Gi exponential minus beta, expanding the exponential. Now in place of E or I, whatever it is, now I can write, what I can write? Epsilon A N or epsilon B N. Agreed? Now I solve here. So I can write like that, exponential minus beta, and I am taking different state, 1, 2 state like that. So epsilon A0 plus epsilon B0 plus simple mathematics, B epsilon A0 plus next step B1 plus epsilon minus epsilon A0 first level B2 like that. Similarly, epsilon A1, just from 0 then 1 then 2. I am just giving simple example, B0 plus epsilon A1 plus epsilon B1 plus that epsilon A2, sorry A1, I am talking about epsilon B2. Then I am proceeding to 2. A2 epsilon B0 plus epsilon, just for 2 B1 epsilon B A2 plus epsilon B2. So because there are two systems, energy is A and B, and I am talking about the 3 states. So last step, I can remove all these things. So what I can write like that, now if you see these things very carefully, epsilon minus B E A0 plus, for second case, epsilon minus B E A1, another state, different states, epsilon B A2 I'm just removing all these things. Red color, because now I'm talking about this second part. Similarly, second ensemble B beta E B0 plus beta E B1 step B E B2 step. So now just you think over the individual system. Canonical is the whole system. So it is actually nothing, the summation. Summation of one state is 0 state, 1 state, 2 state. So it is nothing. It is the partition function, but it is for A. And again for another system B, but again there are three states, individual BU0, B1, B2. So what I can write, Q B, or if I am talking about the Z, if I think Z, small z, A, small z, B, here is capital Z or capital Q. So what I am getting, मुझे क्या मिला, Z is equal to small z A, small z B. But you know the system molecules, Avogadro number, there are a large number of molecules are there. So that is the common state, capital Z equal to small z, and in place of A and B, these are actually like summation of Ni, like that. So it is small n. So this small z or small q is the molecular partition function. Condition is that this is for distinguishable particle, non-interacting particle. But if it is identical particle, indistinguishable particles, then of course this capital Z is equal to Z n divided by n fact. So in fact all these statistical mechanics, whether it is a Fermi-Dirac or Bose-Einstein, will concept this thing. So let me summarize that today I have used, so this part, you see that Z is equal to Z by n, and if it is an indistinguishable particle, this is divided by Ni, total number of particles. Again, just to cross it. This one? Yes. So my dear friends, with this short lecture, this is the lecture number 2 of the statistical mechanics. इस लेक्चर में मैंने आपको बहुत संक्षेप में, बहुत सिंपल मेथड से आपको मैं पार्टीशन फंक्शन की डेफिनेशन, पार्टीशन फंक्शन का सिंपल डेरिवेशन, इज द सम, आप बस इतना जानिए, इज द मोस्ट प्रोबेबल डिस्ट्रीब्यूशन मॉलिक्यूल्स अमॉन्ग द डिफरेंट एनर्जी लेवल्स में मॉलिक्यूल्स का किस तरह से डिस्ट्रीब्यूशन होता है। और फर्स्ट पार्ट में मैंने आपको बताया था, एक डायग्राम से बताया था कि इलेक्ट्रॉनिक एनर्जी लेवल्स क्या होता है, वाइब्रेशनल एनर्जी लेवल्स क्या होता है, रोटेशनल एनर्जी लेवल्स क्या होता है, एंड उसको हम वाइब्रेशनल में हमने विल यूज़ दी, यू नो दैट इफ यू आर टॉकिंग अबाउट द वाइब्रेशनल partition function of the vibrational energy, sometimes the UV visual spectroscopy depends on that. Sometimes it's rotational, sometimes it depends upon the IR spectroscopy and other things. There are different types of things are there. Sometimes we use the rigid rotator, sometimes we will use that harmonic oscillator for in order to calculate all the partition function. और मैंने ये भी बहुत संक्षेप में आपको बताया कि कैनोनिकल पार्टीशन फंक्शन क्या होता है, और उसको समझने के लिए आपको, चूँकि मेरा फर्स्ट लेक्चर को देखना पड़ेगा, दैट इज़ कॉल्ड दी कैनोनिकल एंसेंबल, माइक्रो कैनोनिकल एंसेंबल, सिस्टम, माइक्रो स्टेट एंड मैक्रो स्टेट। फिर मैंने आपको दोनों का रिलेशनशिप बताया कि व्हाट इज, तो इसमें कोई कंफ्यूज मत होइए, आप फिर से मैं आपको बता रहा हूँ, आप कैपिटल Z भी लिख सकते हैं, स्मॉल z भी लिख सकते हैं, कैपिटल Q भी लिख सकते हैं, स्मॉल, इट इज़ डिपेंड्स अपॉन द बुक्स विच यू विल रिफर, एंड आई विल प्रिफर दैट यू रीड Atkins physical chemistry as well as the Levine physical chemistry, Albert E. Daniels, as well as the thermodynamics for chemists and the Glaston. So in my third lecture, जो मैं नेक्स्ट टाइम में आपको बताऊंगा, कि जैसे कि मैंने आपको बताया था कि अगर आप थोड़ा सोचेंगे, यू नो दी फॉर्मूला ऑफ द पार्टीशन फंक्शन, फिर से मैं एक बार आपको जस्ट टेक होम मैसेज, आई इज इक्वल टू 0 टू आई इज इक्वल टू इनफाइनाइट, जी आई की वैल्यू आपको कैलकुलेट करना पड़ेगा, एंड ई आई अपॉन के टी. सो इफ आई वांट टू कैलकुलेट translational partition function in my next part 3, so I have to substitute the value of translational energy, जो कि आपने particle in one dimensional box, particle in 3 dimensional box, quantum mechanics में आपने पढ़े होंगे, जैसे n स्क्वायर h स्क्वायर. मैं एक उदाहरण आपको दे रहा हूँ अभी, मैं आपको n स्क्वायर लाइक दैट, ट्रांसलेशनल एनर्जी, ई ऑफ ट्रांसलेशन. फिर अगर आपको रोटेशनल पार्टीशन फंक्शन यूज़ करना है तो आपको रोटेशनल एनर्जी की वैल्यूज यहाँ पे लिखना है. आपको वाइब्रेशनल पार्टीशन फंक्शन यूज़ करना है तो वाइब्रेशनल एनर्जी की वैल्यूज यहाँ पे रखना है. एंड देन ऑफ कोर्स डिपेंडिंग अपॉन दी, बिकॉज इन पार्ट ट्रांसलेशनल पार्टीशन वेरी क्लोजली स्पेस, तो जी का कई बार वैल्यू 1 के बराबर हो जाता है या 0 के बराबर हो जाता है. तो पार्टीशन फंक्शन के बाद माई थर्ड लेक्चर विल बी ऑन द डेरिवेशन ऑफ डिफरेंट पार्टीशन फंक्शन, रोटेशनल, ट्रांसलेशनल, वाइब्रेशनल एंड रोटेशनल. थैंक यू वेरी मच.